Okay, hello. Hi. Just one reminder before we start today. Homework 1 is due on Thursday, I believe. And then homework 2 is going to be coming out on Thursday. So we're going to be talking about homework 2 in class on Thursday. It should come as no surprise to you that I'm also going to ask you to write some unit tests on Thursday. That's what I said I was going to do. So come prepared to write some unit tests. You'll have hopefully have some chance time in class to write some of those unit tests so that we can talk about them together. I do want to spend some more time talking about what makes a good unit test, what makes a bad unit test, that kind of stuff. But I am going to expect you to write some tests for the code going forward. That's the idea. That's the hope anyway. Any questions about homework assignment 1 or anything else going on? Yeah.
As far as submitting the completed homework assignments, nothing require more than making sure that your last commits are committed to Bitbucket.
Yep.
Bitbucket.
Commit and push to Bitbucket. You're good to go. If you can see your code on Bitbucket, then I can see your code on Bitbucket.
I guess I have one other question as regards to next Thursday. For the unit test we're writing, I don't know where they're going to go.
Oh, we'll take care of that. I'll take care of all that before Thursday. We'll go through it together in class on Thursday. Yep. Question? Yes. That's what it says on the write-up. That's what I intend to do. Yes. Any other questions about the homework assignments or anything else before we hop into today's material? Yes.
Does it need to pass the unit test that you wrote?
Needs to pass the unit test that I gave to you. So that big old file with, I don't even know how many are in there, 15 or so, somewhere in that ballpark. Those are the tests that are going to be used to grade your assignment. Yes. There is a rubric actually on the write-up as well that has point values, so you can have a rough idea of what those tests are actually worth as well. Any other questions? Any other questions? Okay, so today we're going to talk about SQL, the language. We've actually come a long way already if you think about it. We started the semester at the very lowest part of the database, talking about files, talking about binary information, bits and bytes. We've worked our way up through the heap pages and the heap files. Then recently we've been talking about things like relations and relational operations. And then we're working our way up even higher to the part where we're going to be interfacing, we're going to be writing queries against this database. And so the idea that I want to talk to you about today is how do I take a query, a SQL query, and actually figure out what it wants me to do, right? And translate that into those relational operations that we talked about last week in class. That's the goal of today. Now, this is not a programming languages course, right? This is a database course. However, in order to have this conversation, we do need to talk about some concepts that you probably would normally see in a programming languages course. There's just not an easy way to do that. I don't expect any of you to have had a programming languages course before you walk in the door. It's not a prerequisite or anything. I'm not going to go nearly to the level of detail that I would if this was a programming languages course. So if today's material kind of freaks you out a little bit, just take a couple deep breaths, relax, right? We're talking about basically the bare minimum amount of stuff that we need in order to have a discussion about these SQL queries. Again, the important part for me, the main takeaway for me is how do I take a SQL query, a piece of code that we wrote to execute some query, and turn that into a set of relational operations that can be performed that will grab the results of that particular query. That is my goal. So let's talk about how we actually process languages in general, and then we'll take a look at how we are actually going to process SQL code. In general, the act of processing a language is known as parsing. So you're used to writing in languages like Java or C or Python, right? For example, and there are certain rules that are expected of you when you write in those languages, that the computer is going to expect you to follow as you write those languages. Parsing basically says, the act of parsing basically says, is this piece of code that you wrote, is this program that you're asking me to execute, is it a valid Java program? Is it a valid SQL query? Right? It's not trying to decipher the meaning of that program. It's not trying to figure out what you're trying to do with that program. It's just asking the question, do I understand this, right? Does the program make sense? Yes? Well, syntax is part of it, yes. That is definitely in the realm that we're in. But it also includes something called a grammar that we're going to talk about a little bit as well. But not the semantics, that's correct. We're not worried about the actual meaning at this point. So there's multiple techniques for parsing languages. Again, if this were a compiler's course or a programming languages course, I would spend weeks talking to you about this topic. It is a huge topic. We don't have weeks. I'm not going to spend weeks talking about this. It's a databases class. We're going to spend about an hour talking about how to parse SQL in particular. So multiple techniques, top down and bottom up, which actually deal with a tree structure that we haven't quite got to yet. Although you can see it's the next thing to talk about on my list. Basically, how do I construct the parse tree? Do I construct it from the bottom, working my way to the top, or do I construct it from the top, working my way to the bottom? For this class, I don't even necessarily care which one we're using for SQL. It's not important to me. What's important to me is that you understand that parsing is the act of taking a look at a SQL query and constructing a parse tree out of it, making a parse tree. Now, I want to make it very, very, very clear. A parse tree is not a query tree. A query tree is actually what we're trying to get to. A query tree is our goal. That is our destination. A parse tree simply says, I understand, or this is a valid query, right? This query works. If I can make a parse tree successfully, I have a valid query. If I can't, if something screws up, then somebody did not write the query properly. Did not follow the rules of the language to write the query properly. So we use grammars to dictate how a language is parsed. Grammars have a few parts. We see rules, and those rules are based on tokens, and also there are some non-token values that we expect to see as part of our grammar as well. I'll show you an example of a very simplified SQL grammar on the next slide that will hopefully make that point a little bit clearer. The tokens are the actual code. So you can think of a token as the smallest possible thing that I could write that still means something, that still has some kind of meaning behind it. So in most languages, what does that really mean? It means like a single word. So select is a token. From is a token. The name of a column is a token. A comma is a token, right? Commas have meaning in our languages. They do stuff for us. And so a grammar is not necessarily telling us what words I am or am not allowed to say, although it does kind of do that as well. It's really trying to tell us what order is acceptable for those tokens to appear in. I can say a word, or I can speak sentences in English that are syntactically correct. They have all the proper punctuation and everything, but don't make any sense because the grammar is out of order. The grammar doesn't make sense. So we're interested in not just do you have all the proper syntax, do you have all the commas and punctuation that you would expect, but also do the tokens appear in an order that makes sense? So let's take a look at a very, 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 very simplified grammar for a select statement. This is far from complete, but for our purposes, it actually covers most of the bases. I start with a query. That query, I'm saying, for this example, this actually is already a deviation from what we would expect in real life, but for this example, I'm saying that a query is consisted of 4 clauses: select, from, where, and group by. In actuality, we know that actually the only two clauses that are truly required are select and from. The where and the group by are not required, right? They are not strictly required. But for the sake of this simplified example, we're going to say that I expect them to show up. And so you'll notice that after the select, the from, the where, and the group by, I have these, they're not tokens, they're not part of the language, but they're grammar rules. So a select item, what can a select item be? It can be a single column, or it can be a column, comma separated, with another select item. It just allows me to specify as many columns as I want, right? I can make a list of columns using that particular rule. From item is kind of the same way, although it's a little bit more complicated because we introduced the concept of joins last week. So a from item could be a single table, or the other rule that's listed there is that a from item could be a table followed by a join item. There could be a join that comes after that table. And then what makes it even more complicated is that joins have a specific structure to themselves, right? They expect join table on an expression, right? And actually I can chain joins together as well. So I might have multiple join items if I'm joining multiple tables in the same query. This grammar allows for that. And then finally, last, just a simple, very, very simple way of defining an expression is just two columns with an operator in the middle. So where an operator could be equals, greater than, less than, things like that. So words like select item, from item, again, those aren't tokens. Those aren't part of the SQL language. Those are part of the SQL grammar. Those are tools that we use as we parse a SQL query to see if it conforms to the language, see if it conforms to the grammar that we're expecting. So we can use these rules. We can use these rules to construct a parse tree, and I'd like to do a very simple example to show how that might work. Now, I already mentioned that this grammar is not the exact same one that you would expect to find on a SQL database. That part up top with the where and the group by are, that's a little iffy. You'll notice actually in the example that I have here, there is no where or group by because they're not strictly required. But I wanted to pick something very simple to start with just to show you what we might do. Grab some chalk. So I always start with a query. That's my starting point, is a query. So that's going to be the first part of my parse tree. And from there, I expect certain pieces. In this particular case, I just have the select item, the from, and the from item. Now, if I had a where and a group by in this particular example, I don't. But if I did have a where and a group by in this particular example, I would want to include those as well. But I don't. And so I'm trying to pick the rule that most closely matches the query that I'm processing. So, as an example, I have this select item in a tree. This is a token, right? This guy is a token. That's actually part of the SQL language. That's a word that we can code. This is also a token. So as far as I'm concerned, these nodes are not going to have any children. We're done. I've hit a token. This is the bottom of the tree. But these are not tokens. These are part of the grammar. So I have to keep going until I fill out all of the tokens of the query. So for a select item, I've got two possible paths I could take. I could do column followed by another select item, or I could just do a single column. In this particular case, I have two columns. So I know I'm going to have to take the second rule that's listed, column followed by a select item, where the column is, what was the column? First name. First name. Select item. Right? I have to have both of these pieces. This now is a token. Right? First name is a token. That's part of the, not part of the language, but certainly part of the query that I've read and processed. And actually, if we wanted to be fully complete here, there would be a comma as well as a token that I read in. A comma. This other select item we can use to pick up the second column in my query, so that last name column. And there are no select items after that, so I'm just going to stop there. And you can see that I'm sort of piecing this query together, right, as we go. And I'm using these rules to help me do it. I can't just make any children that I want here. I have to make children of that node that conform to the rules that are available to me in the parse tree, in the grammar. And so for from, this is a very simple example. We don't have any joins, I don't believe. No, we don't have any joins. We just have a single table called employees. So the child of the from item would be employees. This is the parse tree for this particular query using the grammar that was on the previous slide. Again, we start with the query. We always start with the same non-terminal. We choose a rule that most closely matches the query that we're trying to parse, and then we add those children to the tree. Sometimes that's going to lead us to have more, we call these non-terminals in our tree, in which case I have to look at those, pick the appropriate rule, right, to make more children, until eventually I've covered every single piece of the query. Does that make sense? So I've constructed a parse tree, and again, all a parse tree tells me is that this is a valid SQL query. This query is valid. I should be able to run this. I don't know how yet. I haven't gotten there, right? I don't know how to run this query, but I should be able to run this query. Are there any questions? Okay. So let's take a look at the next step. If we know that we can construct a parse tree, then we know the query is valid, but how do we execute it? We have to transform this parse tree into something more useful. Like what? What's our goal? Query tree is our goal. So now that excuse me, now that I have a parse tree, now that I know I have a valid query, now I'm going to try and figure out what this query is actually asking me to do. Now I'm going to take a look at the semantics, try and figure out the meaning of this thing. I want to take this parse tree and I want to convert it into a query tree. So you remember a query tree looks significantly different from this, right? Query tree doesn't have it, doesn't have these tokens at all. Query tree doesn't care about commas, whether you have the right number of commas in your query. That's not what a query tree is interested in. Query tree is interested in what? What do I see in a query tree? Yeah. Relational operations. Relational operations, right? That's what I'm expecting to find in a query tree. So how? How do we do this? That's actually a long answer. It's a very long answer. I believe that that's, in fact, probably a bit too long of an answer for me to get to fully in a single class period, but I'm going to at least give you a little bit of a taste how we get there. Just a small taste about how we can manage that process. We're going to use something called a visitor pattern. This is a design pattern often used with trees, often used with parse trees, but really could be used with any tree-like structure that you may run across as you're coding things up. The idea is this. I'm going to take the nodes that are in my parse tree and I'm going to categorize them using interfaces and possibly inheritance, but most often we're going to use a lot of interfaces to categorize them. So for example, right, I might look at, you know, a node in my parse tree. Which one do I want to look at? Maybe like this one here, the employees table. So as I construct this tree, what type of node is this? What type of node is this? Well, the obvious answer is it's a table node, right? But I could also classify that as a relation. Those two aren't exactly the same thing, right? They're subtly different. So maybe I would apply an interface to this that also implies that it's a relation as well as a table. And I could also apply an interface to this that tells me that not only is it a table, not only is it a relation, but this is a like a variable name almost, right? This isn't part of the SQL language. It's a name of a table in a database. And so we're going to look at all of the nodes, all of the terminal nodes of our tree, and try to categorize them in various ways. And what that allows us to do is then it allows us to write visitor patterns to locate nodes that are of interest to us. So if I'm trying to construct a query tree, for example, what's at the bottom of my query tree? If I construct a query tree, what do I see at the bottom? Oh, we just did this a few days ago. We're going to do some more today. What do I see at the bottom? Tables. I see the tables in the circles. So if I'm looking for all of the tables that are referenced in a query, right, I could write a visitor pattern that says traverse this tree, find all of the nodes that are labeled as tables that have a table interface on them. And once you find those, construct nodes in the query tree for those. I might not know how they're going to be hooked up yet, right? But I'm going to make those nodes, and as I add more and more nodes to my query tree, I can connect them appropriately. I might say things like, go find a where clause, right? I'm interested in processing. What's the relational operation that goes with where clause? It's a select operation, right? I want to know what select operations need to go in my query tree. So make a visitor that goes to see if it can find a where clause. Maybe there isn't one, but if there is, I want you to go find where that where clause is so that I can make that relational operation. Go see if there's any aggregates. That's the example that's listed on the slide, right? So here I have these select items. Some of these might be aggregates. Actually, the two that we have are not. But some of these might have average or sum or max or min appended to them. I could write a visitor that's going to traverse the tree and look specifically at these nodes to see if there are any aggregates available so that I can add the relational operations for aggregations into my query tree. This means that I'm actually making multiple passes over this parse tree, right? I'm not just processing it once. I'm processing it many times, looking for each of the individual pieces of the query tree that I want. Does that make sense? I'm going to show you actually a visitor class as part of your homework 2 assignment on Thursday. I'm not going to ask you to write one, but I am going to show you one and expect you to understand what it's doing. So we'll see an example of that in class on Thursday. So if you want to create a visitor, what would you do? You're going to create a visitor class, and a visitor class traditionally just contains a method or multiple methods called visit. That's it. Those are the only methods that I expect to find in a visitor class. Methods called visit. The parameter of the visit method is going to be the node types that we are interested in processing. So if I'm making a visitor to process aggregates, which is actually a visitor that I created for homework 2, right? I'm going to create a visitor for processing aggregates. It's going to have visit methods that are looking for sum nodes, average nodes, things like that. as we traverse the tree then, we're going to look for nodes that match the types that we're interested in, starting with the most specific type. So if I look at this node, an aggregation would be a much more specific thing for me to deal with than just a general column, right? Which would be even more specific than a select item, which could be actually various other things as well. So I'm going to start by trying to find a visit method that matches a specific type here. And if that doesn't work, I might try to see if there's a less specific type. And there may not be a type that matches at all, in which case I might just say, all right, move on to the next thing. We use a process called reflection for this. Is anybody familiar with the concept of reflection? Reflection is a process that allows you to determine the type of an object at runtime. It does not use, what is the Java keyword, instance of? Ugh, instance of kind of stinks. Please don't use instance of in your code. It's bad practice, bad practice. There is a reflection library that is specifically for determining the types of objects at runtime. But once I've found a node that I'm interested in, then the code in the body of that visit node says what I should do based on that. So it may look at, if I'm processing relations, I find a table over here. Okay, what's the name of this? I'm going to create a node for this particular table in my query tree. Oh, I'm performing a join, right? I found a join node in the parse tree. All right, I'm going to look and see what the relations are, make sure those nodes exist, and connect them up with the join relational operation in my query tree. And if I keep doing that, if I keep making those passes for the operations that we care about, eventually I'll end up with a complete query tree, which we can kind of run through a simple query tree. This is not a complicated query tree by any stretch of the imagination, but just for completeness sake, we can construct the query tree for the simple example that we have up on the board. So I want to construct a query tree. We actually already just recently said that what we expect to find at the bottom of a query tree is tables, right? So the first pass that I'm going to take through this is asking for any tables that exist. And I'm going to find one. I'm going to find this node in the parse tree. I know it's a table because it's attached to the from clause, right? It's a from item. So I'll find that node and I'll construct that node in my query tree. What's the next, or I'm sorry, we talked about this in class last week. What clauses do I expect to be executed next? We did the from clause first. What clause would I like to do next? If it exists. Yeah. Where is what I would like to do next? So I'll do a pass over the query tree, or I might just go to the query tree and be like, hey, do you have a where clause? Not the query tree. Sorry, I misspoke. The parse tree. I'm going to go to the parse tree and say, hey, do you have a where clause? It's either going to say yes or no, right? It's going to say, here you go. Here's the node with all the stuff in the where clause. Do whatever you want with it. Or it's going to say, I don't know what you're talking about. I don't have one of those. In this case, that's what's going to happen, right? We don't know. There's no where clause for us to deal with. What's the next clause that I'm going to probably try to do? We did from, we did where. What's the next clause in the order of operations of a query? Typically, group by, which kind of goes hand in hand with another clause. Can't have a group by unless something else happens. What do I need to make a group by work? Yeah. I need a select, more specifically, I need some aggregates. Group by cannot operate without aggregations. So that could be the next thing that we look for. See if there's a group by clause. If there is, then I know there's going to be some aggregates in there somewhere, right? There have to be. if there is no group by clause, there might still be aggregates, right? A group by clause is not required. There might still be aggregates, which I might run into as I process the select clause. So I'll process the select clause, and as I go through and visit each of the columns that are listed, I'll see if there's aggregates attached to those columns or not. And if I do run into an aggregate, I can add that to my tree, right? We saw how to do that with the relational operations last time. There is no aggregation here, though, actually, for us to worry about. We just have regular old columns. So if I come across a regular old column, what relational operation is that telling me to include? The select clause matches up with what relational operation? Project. The project operation. Which Greek letter is that? That is the Greek letter, is that pi? I got two of them. First name, last name. And actually, in our case, we're done, right? This is a simple query. I went through some steps. There were some extra steps that didn't apply to us because we didn't have a group by, we didn't have a where clause to worry about for this particular statement. We didn't have any joins, right, to worry about for this particular query. If I had, it would have been a bit more involved to construct this query tree, but this is a simple example. I was able to construct the query tree with just a couple of steps. Are there any questions about that? So the reason why I'm talking about all of this is because on homework 2, actually, what's going to happen, I'll talk to you more about this on Thursday, is you're actually going to have a database implementation at the end of homework 2 that can accept a query, a very simple query, not every query, right? Very simple queries that don't do too much stuff, basically the stuff that we've talked about. Joins, group bys, aggregations, where clauses are all fair game. I'm going to give you the parse tree. I'm not going to ask you to make the parse tree. That's outside the scope of this class. But I'll give you the parse tree, and I'm going to expect you to figure out from this parse tree what relational operations need to be executed to execute that query. And then you'll actually execute those relational operations as well. That's part of homework 2. That's what we've been building up to for the last couple of weeks. And I'll show you some visitor patterns and all that fun stuff as well. Does anybody have any questions? Let me see where we're at in this slide. Okay, yeah. So once we've finished processing the parse tree, we get this query tree back out, which tells us how we can actually execute the query. So from there, I just perform the relational operations that are specified in the query tree, and I'm done. I have my result sets. But oh yeah, and in practice, this is called an execution plan, not necessarily a query tree. You actually can see the execution plan for a particular query, and I believe that I gave instructions on how to do this in Studio 3, which you now have all of the knowledge necessary to complete Studio 3 if you're working on those studios. That's something you can take a look at on the website if you're interested. But are we really done? And the answer is actually no. After I construct the query tree, I still have more work to do. I want to optimize. I want to focus on performance. And so that's going to be what we talk about between now and the midterm, basically, is, all right, we've figured out how to execute queries, but how can we execute them fast? How can we get good performance out of that query execution? That's our goal between now and the midterm. So we're not going to talk about that today, but there is a set of steps that we will talk about after actually starting next week that will allow us to optimize that query tree. So we're not technically done, but as far as homework 2 is concerned, we're going to stop there. What I have actually for the rest of the day is a bunch of practice problems for us to work on that cover not just this stuff, but also stuff from last week as well about relational operations, just to give you guys a whole bunch of reinforcement heading into homework 2. Before I do that, I want to just pause one more time and see, is there any questions about what we've talked about so far today? Because we're going to be doing some practice for the rest of the day today. We're going to write some SQL queries. We're going to create some query trees. I might have you create a parse tree or two, possibly. That's what's on the agenda for the rest of the day. Any questions? All right, let's do some practice. All right. Yeah, let's start with the good one. This is actually the practice problem that I showed you at the end of class. That would have been last Thursday, I guess, is when we looked at this. And I have an admission to make. I botched it. I screwed it up. I totally blew it. Well, not totally, but I kind of blew it, I guess. I did not approach this problem correctly. I messed it up. So I wanted to make sure that we got this problem right and that everybody understands where we're at with this problem. It's tricky. It's tricky, and I'm not saying that just to, make excuses for me screwing up last week. It actually is a tricky problem. As a refresher, we have this ER diagram here. I don't know if I can zoom in on that anymore so you guys can see it a little easier. We have this ER diagram here, and I want to write a query that does something that sounds very simple. I just want to see who the manager is of each employee in the database. That's it. That's all I want to see. Seems like a simple request. Seems like it shouldn't be that complicated, but it actually is a little bit complicated. So I gave you a hint. You're going to need a join. Probably a join on multiple tables. We'll talk about relational operations and constructing a query tree once we actually have the query nailed down, because that was the part I screwed up. I messed up the query in class last week, so I want to get it right. Let's do this together, and then we can talk about constructing the query tree and do the other stuff. So if I look at this ER diagram, the tables of interest that we identified last week were the employees table, obviously, the department manager table, and the, what's this one called? Department employee table. What kind of tables are department manager and department employee again? There's a special kind of tables. Yeah. They're linking tables. They're part of a many-to-many relationship. Those are linking tables. We can still use them, right? They're still perfectly good tables with lots of good information in there. We can still use them. But they're linking tables. So I want to get a query that has the name of the manager for every employee in the database. And the idea was we could use those 3 tables to pull it off. I actually think we may not need all 3 of those tables, though. No, we do. I'm sorry, I take that back. What I meant to say was, I think we might need one of those tables more than one time. I think we might need one of those tables more than once. And let me explain why I think that. I want each record in my results set to have 2 names, right? The manager name and the employee name. The employees table, if I just include the employees table, that gives me 1 name. But how do I get 2 names out of that? Yeah.
You gotta go back and forth again to find the manager's name.
I gotta double dip into employees to get the manager's name back out. So this is gonna sound really weird, and this is what I meant when I said this is a tricky problem. I think we're gonna join the employees table twice. Once for the manager's name and once for the employee's name. This is a complicated problem. It's called a self-join. I can join a table to itself. That is actually a valid SQL thing to do. Does not happen very often. In fact, this is pretty much the textbook case for when it does happen. Joining a table to itself. But let's see, let's take another stab at it. I think we were pretty close with the query that we had on Thursday. We just didn't go quite far enough to get there. So let's just start over from scratch. I'm not even going to look at what we did on Thursday. I'm just going to start over from scratch. I want this to have first name and last name, but I want it actually to have two of them, right? Two first names and two last names. And they both are going to come from the same table, the employees table. This query, the way I've got it written, already looks like something strange is going on, right? In fact, this is not correct. I'm going to tell you that right now. Let's take a look at the from clause for a second, and then we'll come back and see what we can do about this. Because this doesn't feel right. I hope it doesn't feel right, because it's not. It's not right. So let's put a pin in that for a second and look at the from clause. How am I going to stitch these tables together to answer the question? So last time we joined all three of those tables together, right? We joined all three of those tables together. So let's just start there. We did employees and we joined, I'm not sure which one we joined first. It doesn't really matter. Remember, the order that we joined the tables together actually does not matter. I can switch the order that I joined the tables in and I still get to the same place. For inner joins it anyway. That is true. So I'll join department employees on. And the key that's in common for these is employee number, all right? Okay, and then I'll join the other table that we talked about, which is the managers table, department manager. On. I'll join it on the department number from department manager. Equals the department number from, or I'm sorry, it's employee number from department manager. My fault. Sorry about that. Employee number from department manager equals the employee number from employees. All right, I feel like this is roughly how far we got on Thursday, which is a good start, but does not go far enough. I'm making the claim now that we need to join the employees table again, a second time, to make this happen. How? Is it going to be any different than the first time that we did it? So the first time we joined it based on department employee, right? Actually, we did it to both, employees, employee number. So how am I joining it? What's the join condition, I guess, is the big question. Does it matter? I'm going to join employees again. But the question is, what's my condition this time? How do I make that connection between the manager and the actual employees? So the way I have it, if we pretend like I didn't do this yet, pretend like I didn't do this yet, I can see who's a manager, right? Here's a manager, employees.employee number. What I need to do is match the department number here to the individual employees, which is over here, right? So how do I do that? It's a little tricky. Yeah.
Let's see. I was thinking. Well, I think the first join would be the same, but then but the second time it's going to be join department manager on where department manager department number employee
Employees doesn't have a department number, though. That's part of the problem that we're running into.
Well, and then the second line, like you would start off the same way, like you still do join department employee on employees employee number equals department employees employee number. Then you join that on by department number.
Okay, let's try to make life a little bit easier for us. I've got employees up here twice, but actually they mean two different things, right? One is truly employees, but the other one I'm intending to mean the managers. I'm just trying to find the managers, right? Just trying to find the managers. So let's say that in our query. I can rename stuff in my query. What's the word that I use to rename stuff? As. So let's rename at least one of these in my query to say what we really mean. This one's joined to department employees. This one's also joined to department manager. Yes. So since I've joined this one to department manager already, I feel like this is my managers table. As managers. Join. And what that means is anywhere that I used employees so far is actually not employees anymore. It's managers now. Here. Managers. Okay? And now when I join the employees table a second time, right? Now when I join this employees table a second time, I can try to hook up those department numbers. So the department number of, well, it's going to join employees. This is still a tricky problem. How do we get those two hooked up? The department number from departments, employees. Oh, I think I know what to do. I think it just clicked in my brain finally, after staring at it for long enough. We'll hook it up to the department employees table again. Equals and then to really solve the problem, we can tack a where on. Where department emp dot depno equals department manager dep. No. This is the magic right here. Using this where clause to hook up the department numbers from the employees table to the managers table. That's the magic. Yes?
You said as managers before we department employee table, department manager table.
Yep. As managers. But then I changed this to say managers too to reflect that name change. And that actually solves our original problem as well. Now when I say first name, last name, I actually have more information that I can provide. I can say not just select first name, last name, but select managers, F name, managers dot L name, and then employees dot first name, I don't have space. This is a beast of a query. Sorry. Sorry that I ran out of space for that one. But this renaming this table managers also solves our problem here, right? Also solves the problem of how we can distinguish between the manager's first name and last name and the employee's first name and last name. So let's take a minute to recap, because look at this query. Oh my gosh, what have we done? We've created a monster. I've joined the employees table to the department employees table and the department managers table. I need those two tables to tell me what departments these employees are matched up with and what departments the managers are in charge of. I joined the employees table again to the department employees table. So it's on there twice now, which means that as I perform this join, I'm actually going to see potentially, in practice I don't think this is going to happen, but potentially I could see every employee show up twice in the result set. That's not going to happen in this particular case, but if the conditions were right, that could potentially happen. And then this where clause specifies that the department numbers of the employees have to match the department numbers of the managers to make this happen, to make this work. Sorry if I exploded your brains. That wasn't my intent with this problem. It ended up being a lot more difficult than I anticipated. And let me just go ahead and say right now that I would never ask you to write a query this intense on something like an exam. That's too much. This is way too much. Yeah, I don't want anybody losing sleep over this. This problem took on a life of its own. I wrote a problem that I thought would be simple and straightforward, and it is not. That was not intentional. That was me underestimating how complicated this problem was. But I did want to at least do it justice and finish it properly, since we did not quite get there on Thursday. Are there any questions? Yes?
The only part that kind of scratched my head over is that where clause at the end.
The where clause?
How that works. I mean, okay, like, so it's just where a department employee equals department manager.
So we could try to construct what this would actually look like a little bit. I'm running out of chalkboard space, but I can do my best. What does it look like when we join tables together, right? That's really what we're trying to get at. So, you know, here is F name, L name, employee number, right, from the employees table. So I see all the employee data. I don't care what the actual data is necessarily. And then I'm going to tack on the columns from the other tables that I joined. So department employee gets tacked on. And I'm sorry, I should be writing down the columns, right? Department number actually gets added twice. So I've got department number from the department employees table. And I've got department number from the department managers table as well. And then I add the employee information again a second time because I joined that table a second time, so I don't have room to include it, but first name, last name, employee number shows up. And so the conditions say, well, actually, I only want you to add a row here if these two numbers match up. That's what, right?
Like, yeah, I kind of thought when you got to join, you only end up with one department number, but no, you end up with one.
You end up with one from each table that you've joined on. Yep. And so the where clause allows me to specify that these have to match. And then once these match, I know that, all right, this is the first table I joined. That's going to be my managers. This is the other table that I joined later. That's going to be my employees. And actually, the same manager could show up multiple times, right? Because they're going to have lots of employees. The condition, in other words, is going to match many times. This, you know, the department numbers for each employee, like all the employees that are in the same department, right, are going to have that department number pop up a whole bunch of times. So these are going to match the managers a whole bunch of times as well. And we'll see all the employees listed out per manager. Yeah. Any other questions before we can put this problem to rest? Yes? Oh, yeah, of course. Sorry about that. Take it in all its glory. Look at it. Actually, as bad as this query looks, not even close to the longest query that I've seen. Not even close. SQL queries can escalate rather quickly. Anybody who's done any SQL programming on a regular basis knows that SQL queries can get pretty large code-wise. This one is, I mean, it's not small. I'm not going to pretend like it's simple, but it's also not the most complex, not the largest SQL query I've seen in my life. Any questions? Let's try an easier practice problem. Let's move on from this one. Let's try something a little bit more relevant to us. All right, here's a good one. Now this problem, I promise you right now, this query is a lot shorter than this one. You can take my word for that. It's a lot shorter, but there is a trick. There's a twist. It uses the same ER diagram. I want a list of all the employees who do not have a title. If I asked you to write a query that gave me the list of all employees and their title, I feel like that would be pretty straightforward, but I'm actually kind of asking you the opposite. I want to know all the employees who do not have a title. There is no title. Think about what that means. Think about the operations that we talked about last week and how you might use those to approach this problem. I'm going to give you a few minutes to think about it and talk to your neighbors, and then we'll put the solution up here on the board. Yeah, of course. All right, there's a trick to this one. What's the trick? Does anybody figure it out? Yeah. You have to use an outer join to pull it off. I'm looking for something that doesn't exist. That's a big clue to use an outer join. Why? Why does that make sense? Why does it make sense to use an outer join there? If I use an outer join, what happens? What do I expect to see in my results? Yeah. Null values. Yeah, lots of null values. And so then I can look and see if a null value shows up. That's what I'm looking for, right? That's the result that I want. So let's see if we can piece together the query. I'm looking for employees So the select is straightforward. Just select, I don't know, employee number is fine, right? Or if you want to do first name, last name, that's fine too. It doesn't really matter, right? I know we're going to need two tables, the employees table and the titles table. But the order now kind of matters a little bit, right? The suggestion was to use a left join. Or does the order matter? That's a good question, actually. I mean, it does. Well, let's try it out, and we can talk about it a little bit. I'll just start with employees first. The suggestion was to use a left join titles. And then the join condition seems very straightforward as well, right? It's just on employee number. Oops. Okay, so we've performed the join, but then can I limit this? The question says who don't have a title. So right now, what am I going to see? If I perform this join, I can actually just modify this diagram a little bit. I'm going to see the employees, and for the titles, I'll see there's a title column, right? And if the employee has a title, I'll see the title here. If an employee doesn't have a title, I see null, right? I see null there instead. So the final piece of this is, can I use this to filter my results? Sure can. I need a where clause, but what does that where clause say? Where title equals, yeah. So that's a sort of a common trap that people fall in. Equals null doesn't cut it. On most database systems, this won't work the way that you think that it will. The proper syntax is to say is null. So a slight difference in how you would approach that, yeah.
Well, actually, I was going to ask, if we're wanting to return all the employees who do have a title, like there's a quiz, don't we?
So if we wanted to, yeah, how would this query change if we want to return all the employees who do have a title? How would this query change? Is not null? Actually, I could do even better than that. That would work, but I could do even better. Yeah. Just do an inner join. Get the left out of there. Get the where clause out of there. We're good. Because an inner join only is going to perform the join if the foreign key, primary key, shows up on both sides, right? And that's only going to happen if there's a title to be shown, particular employee. Could I swap the order of these tables and get there? Now, you said yes, and that's correct, but I'm wondering why you said yes. Is it because you could change this to say right? Because I don't like that answer. Could I keep this as a left join and swap the two tables and still get there? Could I swap these two tables, keep this as a left join, and still get there? What do we think? Yeah.
I think you could, but you'd have to change the where clause.
Have to change the where clause? Okay.
Wait. Yeah, I can.
So think about what that means. I'm not going to see nulls in this column anymore, right? If I swap the tables, I'll see nulls over here instead. So what employees am I going to see over here? The nulls are going to be for titles that don't have an employee, which, I don't know, I guess could happen. It's a little odd, but it could happen, right? The employees that I'm going to see over here are only the employees that have a title. The employees who don't have a title aren't even going to show up because of the way that join works. It has to be this way. It has to be this way. If I want to flip the order of the tables, this has to become a right join in order for this problem to work. if I flip the order of the tables and leave this as a left join, I don't see a path to get there. I don't see a path to get there. So for inner joins, the order I join them in doesn't really matter. But for outer joins, very much does. Very, very, very much does. What if I wanted to do a query tree for this guy? It wasn't part of the problem, but I could. We could do it real quick. It'd be a good exercise. See if I can get this up there. If I want to do a query tree for this guy. What comes first in the query tree? I start at the bottom, right? With tables. I've got two tables. I've got employees and I've got titles. So all right. What am I going to look at next? There's a join here, right? We didn't talk about outer joins, though. This is a good time to bring it up real quick. We talked about how to do inner joins on this tree. Inner join symbol was this guy. It's called a bow tie. And then I'd put the condition here, right? Employee number equals employee number. So if I was doing an inner join, this would work. The symbol for an outer join, specifically a left outer join, you just add a little bit of a thing over here to the bow tie to make it work. I don't know what that's called. There's probably a name for it. I just call it a little thing. I don't know. I don't know what it's called. A right outer join would be, on the right side, and if it was a full outer join, I'd put them on both to indicate that I've got an outer join there. So that's what the symbol is for an outer join. If you come across that. What's next on my query tree? Yeah. Projection. So we're doing the select clause next. Is that right?
Oh, no.
Usually we do where. Yeah, usually we do where next. I mean, honestly, though, they both get us to the same place. It's just where's a little faster performance-wise. So if you did project next, wouldn't necessarily be incorrect if you didn't care about whether it was close to optimal or not, right? Either way. But we were going to, so select, which is, I think it's that guy, right? Title is null. And then the project, which is pi, employee number. There we go. There's the query tree for this guy. The main reason I did that was just to show you the outer join operation. The left join operation. Any questions on that one? I got a couple more examples left. I think we have time for at least one more. We did that one already. Let's not do that one. Let's do something a little different maybe. Can you guys read this okay or no? No? Let me see if I can zoom in. Hang on. Better, worse? I really want to do this problem if we can. This is a relational algebra expression. I could even put it up on the board if that would help. Got another bow tie operation. This time it's on courses. Let me just move this down to the next line. another one. I don't know. This one is on departments. Course. And then comp sci. Departments. Courses, enrollments, students. So the question is, with this relational expression, can we construct the original SQL query? Can you write the SQL query based off of this? We only got about 5 minutes left, but take a minute or two, see if you can start piecing it together if you haven't done so already. All right, we don't have a ton of time left, but if you're approached with this problem, what are you going to look at? How are you going to try and reverse engineer it, I guess, back to the SQL query? We have to pay attention to the relational operations that are being performed, right? So what clauses am I going to see in my query that I need to write? There are two that are required. Select and from. Those are not optional. Are there any other queries that I'm going to expect to see here based on what you... Where? There's a where clause. I know that because there's a relational select. So there's definitely a where clause. Ugh. Okay, so now that I know what clauses exist, I can go back and try to fill them in. What am I selecting? SID. It's the first thing that we see. The from clause. How many tables? Looks like 4. There's a 4-table join. We only got 2 minutes left and my arm hurts, so I'm not writing that one out right now. 4-table join. Again, that might feel like a lot. Like, oh my gosh, I'm joining 4 tables together. Actually, that's not terribly uncommon to see. And then the where clause is that select operation, department name, computer science. So if you piece together this 4-table join in here, this would be the query. You can also kind of see the query tree in here, can't you? A little bit in this statement. I think you at least could construct a query tree based off of this expression. There were a couple other practice problems that we just didn't have time to get to. So here's one about design, creating an ER diagram, and there was another one that I skipped about creating a parse tree and a query tree for a particular query. I would love to have a chat with you about those in office hours tomorrow if you are interested in going over them. I'll be there tomorrow at the usual times that are posted on the website. Come by and say hello. Come by and talk to me, or I imagine a lot of you might be coming by to talk to me about homework 1 as well. I'm happy to do that. That's going to do it for today, though. Good luck on finishing up the assignment, and we'll talk about assignment 2 on Thursday.